Henriksen and Niels Serup from DICO also. So let me give just a little bit of context here. This work is about data parallelism, and we're basically looking at trying to deal with irregular data parallel problems. So basically, all these SIMD architectures have been driven by demand for high performance, and that opens up this possibility of data parallel programming. There has been a lot of previous work on trying to deal with irregular problems. In particular, Blalock's flattening transformation is providing some very good insights into how we can actually transform a program that is irregular in nature and transform that into flat data parallelism. The problem, however, is that there's a large performance penalty associated with this thing, and it's currently an open research project. A problem how to actually get decent performance out of this in practice. So there might be other solutions, at least in the meantime, until we have good practical transformations that will work. One is to use a pay-as-you-go solution, and what we'll see here is an idea basically based on using high-order functions to capture such design, and we will do that in the context of this Futhark language. Futhark is a strict parallel functional and pure programming language, and at the same time a compiler that's aimed at generating efficient code on massively parallel hardware, such as GPUs. And what we will describe here is this function called expand, which is basically a function that you define as a user based on some simpler segmented operations that we'll describe here. So this function expand is parametric in the types A and B, and then it takes two functions, and then it takes an array of elements and gives you back a possibly larger array of elements. And the two functions that are passed in will basically describe how we will transform elements in the source array into multiple elements in the target array. Let us just consider an example here based on some of Blalock's previous work. So here we have an example where we would like to turn an array of lines into an array of points. And the first thing to notice is, of course, that there will be different work associated with different lengths of lines, right? So one long line will end up being represented as many points in the result, and the shorter lines will have fewer points. That basically constitutes an irregular nested data parallel problem. So before diving into how we can actually get a work-efficient implementation of such an algorithm, let us just have a little bit look at Futhark. So again, this is a strict data parallel pure functional language. It has quite a decent performance numbers, so I won't go into details here, but there have been some papers on that demonstrating that in some cases we can even get, if the problems get big enough, we can basically also outperform algorithms written in the domain-specific language OpenCL and CUDA themselves. And basically, just Futhark does a lot of transformations and aims at doing coalesced memory accesses and so on. And sometimes that is so tedious that the CUDA programmer hasn't done the proper work. And in those cases, we can see that an approach such So Futhark will beat these examples. It does support very well regular nested parallelism by a technique called moderate flattening. We will look at what that is, basically turning these nested regular structures into flat structures of commutation. So just to emphasize a little bit about the language, it is syntactically kind of conceptually like Haskell and ML, and then it has simple sequential mechanisms for writing conditionals and sequential loops. They have a functional semantics, and it also has like you can be specific about the data types underneath, whether you're dealing with booleans, 32-bit floats, or whatever. And then it has a set of second-order array combinators, which all have parallel semantics, but the compiler will look to get us will basically allow it to sequentialize these operations if it sees so. That would be a good idea. And then it does also support higher order functions and even higher order modules as well. So the second order array combinators are the ones you would presume. We have basic maps. You can do map 2, similar to zip width in Haskell. We have reductions, assuming that the operators are associative and there's a neutral element associated with it. We have scans, parallel inclusive prefix scans, and of course that operation is essential for implementing many of these data parallel algorithms and get work-efficient solutions to them. Then of course it has a number of other important parallel constructs like filter and scatter, and a lot of work has gone into actually getting good parameterized kernels inside the Futhark compiler, so that will basically generate very efficient code in many of these cases. So then at the language level, it also has support for being, you can specify that a function is parametric in array sizes. So here's an example of the dot product. You can see here it's parametric in n, meaning that it will take in two arrays and it's presumed that they have the same length, and then it will turn that into an integer. It is enforced at runtime, but of course if it will recognize at compile time that there's a problem, it will tell the user. And then here's, for instance, how we can specify the map2 function. Here is parametric in A, B, and C, and N, and then we can specify in the types that the result array here will be, or vector here will be as big as each of the arguments. Then it has this approach that it will basically eliminate all abstraction features at runtime. That's essential for this particular work we're talking about here, that all these higher order functions will be inlined and eliminated at compile time. So that's the case both for functions and for modules. Other transformations that it applies is that it has this array of structs to structs of arrays transformation, which will leave zip and unzip as becoming no-ops at the end. So let's go back to this line drawing. So how do we actually generate points from these lines and get a work-efficient solution for these? So the first number, as also said before, the number of points on a line we can think of being the maximum of the x range and the y range. So it takes a little bit of thinking. We will see here something that is not as steep. We can basically count basically that's the length of the x range, whereas for something which is steeper, it will be the length of the y range, which will be the number of points that constitute the line. So based on this this idea, and of course the notion of the longer lines, the more work, we have some preliminary functions here and some types we can write up. Each point will basically is represented as a pair. the line is then a pair of points. We have some utility function here for comparing. Also, just to simplify that, basic Futhark is quite simple in nature. We can compute the slope of a line given by the two endpoints. And then there's a utility function here for making a grid, given that we have a height and a width, and we have a number of points. Then that will actually output an integer array with ones in the positions where there's a point and 0 otherwise. Right? So we see here that the size here of the result array is basically defined by the input here. So there's we see here that the values here that are given basically occur in the types here. So there's a simple, at least, notation that will allow us to check the dimensions and so on. Now, to apply this expand function, what we need to do is simply to specify the two functions that are required. So we would like to apply the expand function on first the number of points that each line constitutes to, and then we would like to be able to say, well, given a particular line and the point number in that line, can we then compute the particular point? And it turns out for this kind of problem, like for line drawing, it is indeed possible to do so using these two functions. So point and line will basically just specify here the maximum of the x and the y ranges, and the way to get the points in a line is a little bit more involved. We need to compute the slope, and then there are two cases: either the x dimension is the one that increases the most, or it's a y dimension. And so with that we can then compute the particular point. And now the only thing you need to do to actually get a work-efficient solution here is to apply the expand function and to the point and line function and the get point and line functions that we just defined, and then we will pass in the lines, and we'll get back something we need to unzip, and then we pass that into the make grid function. So also notice here that Futhark has this support for higher order functions, so we have defined these pipe operators here, so they're simply defined in the language as well. So it leads to a Haskell-like syntax. And with that, we basically get a work-efficient version of line drawing, meaning work-efficient means that it will do no more work than a sequential algorithm will do, and it has a depth which is optimal, that it really can be implemented in parallel. So how do we then go about implementing the expand function? So Futhark implements all these, as mentioned, regular parallelism quite well using this model flattening. It basically allows us to have multiple nests of maps, and it will flatten that into one map construct. It also has support for having nests with a number of outer maps and then a reduction inside. That will lead to segmented operations on segmented reductions. And similar for an outer level of maps with scans, with a scan inside. And then it has a lot of fusion machinery to basically do as good as possible, so it doesn't have too many intermediate arrays. But it will leave it up to the programmer. If you have a very irregular parallel structure, it will leave it up to the programmer to flatten this problem himself. There are no support for irregular data structures like regular arrays, and also it's not allowed to do looping within parallel constructs with looping which is irregular inside it. That will turn out to become and checked at runtime if such things happen. Or you will, in some cases, you will just get a lot of thread divergence. The way that that all these flattening, even if you the flattening by expansion, whether you use those techniques or not, you basically need some flattening tools to deal with segmented operations. And let me just describe some of those here. So the first thing to get that you will need is a segmented scan. And it turns out that that's possible to implement. That has been known since 1980, basically based on the ordinary scan operation. That requires that you can deal with operations that are not only on scalars but also on records. So here the trick is to basically have a flag array and pair the data up with the flags, and then you use the flags to guide whether you should reset the scan or not. So let's just consider one example here. So you have the values you need to scan 2, 3, 1, 4, 2, 1, 5, 3, and then you have the flag vectors specifying that these are the points where you want to reset the scans. So the segmented scan here will then compute the scan up to the reset point, meaning 2, 5, and that's a plus scan here with 0 as a neutral element, 2, 5, 6, and then it will reset. And now 4, 6, and then reset 1, 6, 9. Right, so that can be implemented basically at the programmer's level in Futhark using this thing. So we don't need to have a particular implemented segmented scan at the low OpenCL level. Another tool that's needed is segmented IOTA. So segmented IOTA is basically a way for us to based on a flag array and an IOTA, and we've seen some examples of IOTA previously. That's basically the index space 0, 1, 2, 3, 4, and so on. And with a segmented IOTA, we basically allow for resetting this indexing at certain points guided by the flags. So that can be implemented again using a segmented scan, and then a little bit of offsetting at the end using a map. So again, the implementation here is work efficient, and it's based on the segmented scan and a map, meaning that they work really in a data parallel setting. So here we see the result here: 0, 1, 0, 1, 2, 3, 0, 1. So the IOTA reset using the flag vectors here. So that was one of the necessary tools here. The second one, the replicated IOTA, that allows us to basically associate for each target element which source element we actually are dealing with. If you imagine the line example, right? So if you have a particular point, that's associated with a particular line. And we use this replicated IOTA to specify that. So the input to this function is basically a repetition array here. It has a size n. This is the number of elements in the source. And then it will basically produce a result array which is as big as the sum of the repetitions of the values in the repetition array here. And that is then reduced here. I won't go into details here about how it's computed, but just notice that each of these operations are data parallel operations, and they only depend on the size of the eventual result array, but the depth is limited based on using the data parallel constructs. So the end result here is that if we pass it with the arguments 2, 3, 1, 1, we will get 2 zeros, 3 ones, 1, 2, 1, 3. So with these operations, we can then define the expand functions quite easily. What we see here is that in Futhark, in Futhark, we can first define the sizes using a map over the input array using the size functions that's passed in. Based on the sizes, we can then do a replicated iota to get the indexes, and that will basically be the indexes corresponding to the source. And now we can calculate increasing indexes for each source using this iotas here. And at the end, we basically can produce the result array with this map2 thing, which will basically call the get function with the particular input that's given, the particular source element, and then the index of which one which target element we're interested in. So again, this is of course programming using high order functions here, but again, since both size and the get functions are inlined in the generated code, we get really efficient code running on GPUs at the end. There are some tricks that are needed to pull here related to some of the previous talks here. That in Futhark right now, array indexes is not necessarily guaranteed, and in some cases, when Futhark cannot prove that array indexing is sound, then it will scream at the user, and you will need to insert an unsafe yourself around here. We do have one of the backend is a C backend, which is a sequential one. And for that one, we basically have a runtime check. But we're working at mechanism also to capture this thing statically instead of being. But one can see that it's actually quite difficult to track these indexes and see that well the values inside this index array, they will all be lower than whatever is the size of array. So there are some tricky cases here to get that to work. So we really did need some dependent typing and some enriched typing to get this working. So there are other kind of irregular parallel problems than line drawing, of course. One example is to basically turn triangles or circles into an array of lines, and then one can then take those lines and turn them into points. We can also use the expand functions for work efficiency over usefulness. It's in the paper. There's also the example of using sparse representation of matrices, for instance, in the context of matrix vector multiplication. That example is also in the paper. And then there are again some things that are not that trivial to do. For instance, quicksort. So I did do the exercise of implementing that by flattening by hand on those things. So that takes quite a lot of code to do that in Futhark, so you get a flattened version. But that's not currently done using a construct like expand. So that's basically hand flattening. Still runs in Futhark, but Futhark doesn't give you anything. You're basically having a flat model of, and you need to do the flattening by hand. And Niels, of course, will come out with a recursive. You just specify the recursive algorithm, and then it will generate the flattened version for it. So that's some of the limitations. So let's see just very briefly the triangles here. So if we want to take, one can basically have the intuition that if you have a triangles like this, we can basically split this into two triangles, one that has a lower line here and one that has an upper ceiling. And then we can calculate the number of lines that each of these triangles will amount to. And then given the points, we can then compute, similar to what we did with the line thing, we can compute for a particular line, for instance for this one, line number 1, 2, 3, 4, 5, what will be the starting point of that line and what will be the end point of that line. And then based on that, we can use the expand function and pass these two functions in, the number of lines and what is the line defined by a particular index, and then we can use the expand to generate the triangles. I won't go into the details here, but just show here that it's also in the paper. Here we see a picture where this is actually done in real time in a game in Futhark, where they are all small triangles, and they are all using this approach of a flattened approach, where all the triangles, the small triangles, are expanded into lines, and each of the lines are expanded into points, and then we maintain the depth and so on of the color here, and then that means that we can basically have this scene computed on a big screen 15 times a second. It's not to compete with native graphics, but at least I mean it simplifies that it's doable in practice here, and also that there are things in the paper, some performance measurements, basically comparing to doing hand flattening and so on. So that's all available in the paper. There's also some algebraic properties of expand. We can utilize some fusion rules, how it fuses with maps and filter and so on. That's also in the paper. So with that, thank you.
So do you think you can statically determine, do you think you could go from a nestled program to a program that needs to expand statically in the compiler, or do you think this is something that requires a sort of human eureka?
Yeah, so of course we've been thinking about that. One thing I like about the expand thing, maybe that's part of the answer, is that you have a chance at least to think in a little bit different, higher level that, oh, I just need to provide these two functions, then I get something out of it. There are some features basically missing that also from the Futhark implementation. For instance, we don't have recursion right now, so that means that everything has to be rewritten into these loop constructs. Of course, that can be done. It's not that's nice. So that means also that there's some I would say something that needs to be overcome before actually we can see how far it can go. At least I couldn't get something. I could imagine that there would be some kind of higher order functions. Maybe inside the loop you'll need to apply the expand function multiple times, and then you could implement quicksort. You could imagine doing that, right? Also fractal structures, for instance. You could implement using that, but that turns out to not really require irregularity. At each level, you basically know the Sierpinski, for instance. You will always fan into 3 things and 4 things.
And you can also do quicksort with iterative scans, right? So you don't.
Yes, and then of course you could do it just by hand. The whole flattening by hand, yes. But that's still, I think, an open. I just thought this was a particular nice, small thing. That the design pattern is quite elegant and small and not that fancy. So it's interesting that at least for some classes a problem. But of course, this is not the whole story. We need to go beyond these examples and cover